A recent breakthrough in cancer drug development may mark the beginning of the end for one of oncology's most notorious challenges, KRAS. The excitement is being driven in part by emerging clinical data from Pan-KRAS inhibitors, such as Daraxonrasib, a new generation of therapies designed to target multiple KRAS mutations rather than a single genetic subtype. For cancer researchers, this represents a milestone that many believed might never be achieved. To understand why, it helps to appreciate the challenge.
For decades, KRAS was considered undruggable. The reason is often described with a simple analogy. KRAS looked like a cue ball. Most successful drugs work by fitting into grooves, pockets, or crevices on a protein surface. These features provide a place for the drug to bind and exert its effect. KRAS, however, appeared remarkably smooth, offering few obvious footholds for medicinal chemists. Like trying to grab a rolling cue ball, researchers knew the target was important, but had little to hold on to. What made this challenge so significant was KRAS's central role in cellular signaling. KRAS functions as one of the cell's master molecular switches. Located immediately downstream of many growth factor receptors, it receives incoming signals and relays them through pathways such as MAPK and PI3K-AKT, which control cell growth, survival, metabolism, and adaptation. In many ways, KRAS is not only shaped like a cue ball, it acts like one. When activated, it transfers energy throughout the signaling network, setting numerous downstream processes into motion. Under normal circumstances, KRAS cycles between active and inactive states, allowing cells to respond appropriately to their environment. But cancer-causing mutations can lock KRAS into its active state. The cue ball never stops moving. Growth signals continue to flow, driving uncontrolled proliferation and helping tumors survive, evolve, and resist treatment. Because KRAS mutations are found in approximately 90% of pancreatic cancers and large portions of colorectal and lung cancers, researchers have spent decades searching for ways to stop this signaling engine. The first breakthrough came when advances in structural biology revealed small transient pockets that appear as KRAS changes shape. These discoveries led to mutation-specific inhibitors such as sotorasib and adagrasib, proving for the first time that KRAS could be drugged. However, those therapies were limited primarily to tumors harboring the KRAS G12C mutation, leaving many patients without a targeted option.
The first generation of KRAS inhibitors was a historic breakthrough, but it came with an important limitation. Drugs such as sotorasib and adagrasib work by binding a transient pocket found in the inactive form of KRAS G12C. As a result, they are effective against a specific mutation but have limited applicability to the many other KRAS variants that drive cancer. Daraxonrasib takes a broader approach. Rather than relying on a pocket unique to a single KRAS mutation, it is designed to inhibit active KRAS, signaling across multiple mutant variants. In essence, the first-generation drugs exploited a specific weakness in one version of KRAS. Daraxonrasib seeks to control the common signaling activity shared by many KRAS-driven cancers, potentially expanding targeted therapy to a much larger group of patients.